Dear learners, very good afternoon to all of you. This is the first live session for the course Applied Thermodynamics. Myself, Professor Niranjan Sahoo. If you have any queries, please raise your hand or can put in the chat box as well your questions. I hope by this time you will be enjoying this course. Thank you, Sagar. By now, I think we have week 3 is over. Of course, week 4 is over. So shortly we'll start week 5, IC engines. By next week, we'll start IC engines. Till this point of time, we have review of basic thermodynamics and steam power systems. So by next week, we'll start the IC engine course. Now, till this point of time, whatever you have any queries, any part of the lectures, you can raise your questions so that we can start discussing. But anyway, before you keep your discussion on, let me also share some of the things or the questions that were raised during the discussion forums. So our team has compiled everything and we have put it in the form of some of the PPT slides. So I'll just try to share some of the important questions that were raised at different parts of the lectures. So let me go through them one by one. So first of all, on behalf of NPTEL certification course, I invite you all and myself, Niranjan Sahoo. I am professor in the Department of Mechanical Engineering. So in this live session of Applied Thermodynamics, the first questions that were raised in the discussion forum and which was in the lecture number 2, the question was raised about the negative heat. Let me know if real life example of negative heat. As you know that the quantity positive or negative with respect to work or inner energy interactions have certain standard assumptions or standard viewpoints. For example, if you take a system, the system does the work or work done by the system. So work done by the systems, the arrow signs outward of the systems, and this arrow when it goes outwards, work done by the system. In a conventional practice, we say it is a positive quantity. Now, in the same philosophy, the other quantity of energy transfer, which is heat, if it is taken out from the system, then it is a negative quantity. Okay, and in other words, if work is done on the system W, which is a negative quantity because work is done on the systems. And in same philosophy, we must say that heat flows into the systems. U has to be positive. So these two sign conventions has to be taken into account while taking heat and work together. So for outward situation, work transfer is positive, heat transfer is negative. For inward situations, work transfer is negative, heat transfer is positive. But however, the magnitude of work or heat transfer remains same. So one should not get confused whether looking at the direction of arrow mark, one should not get confused. And in the real life, what is the negative heat? Which means that suppose you have a cup of hot coffee and when you keep it in the atmosphere, heat goes out of the systems. So if a coffee cup is taken as the systems, in which the coffee is inside, which is maybe at some temperature, maybe 40-50 degrees centigrade. So when heat goes out of the coffee, so we say it's a negative quantity. In other words, when we are heating a water, so we say that heat is getting added. So that is a positive quantity of heat. As far as the magnitude is concerned, magnitude is as may remain the same. So this concept has to be remembered while taking into consideration of work and heat transfer. And in fact, both are these mode of heat transfer, both are the mode of energy transfer. The next question was raised, what is the first law of thermodynamics? So you'll find in every basic thermodynamic books, you will find these definitions. And for me, I don't have to explain further. So since it was applied thermodynamics course, you might be knowing the concept of basic thermodynamics at UG level. Just for the sake of continuity, I'm explaining is that the first law of thermodynamics for a given process for any type of system in which we are going to apply the energy conservation principle. What it says is that the net change in the total energies of the system during process is equal to the difference in the energy entering and giving during that processes. So here the change in the total energy signifies net change in the potential energy, kinetic energy, internal energy of the systems before and after the commencement of the processes. So any basic thermodynamic books, if we can find the many more details of this law. And the third questions, I think it is question is some typo. I think what is thermodynamic types? There is no such things of what thermodynamic types. Rather, thermodynamic systems may be divided into three types, which I understood. If the learner wants to know what is the type of thermodynamic systems, we have open systems, we have closed systems, we have isolated systems. In a open system, if you say this is a system, there is mass as well as energy interaction is possible. So energy interactions can come from heat or work. So energy interaction is possible. Other way is that we can have mass interaction. So both when the mass enters into the systems, it also carries energy into the systems. So energy, and in that thing we call this as a enthalpy. So in open systems, we have both mass and energy interactions is possible. But when you say closed systems, so if you say system is closed, so we'll arrest the mass transfer. Only system can undergo change of state with respect to energy. That means either it can be work and heat. So this is referred as a closed systems. And third one is isolated systems. So the system remains as it is, and there is no mass, no energy interaction. So when such a thing is there, then we call this as a isolated systems. So if you extend these concepts, systems plus surroundings, which constitutes universe. So the word universe in thermodynamics sense is an extended version which involves mass, which says that there is no mass, no energy interactions. So we call this as an isolated systems. Next question was somewhere in the lecture number 1, we might have used the word IC engines or CI engines. So in fact, it was answered by Mr. Anurag. Thank you for these answers. We all know that IC engines is internal combustion engines. It is divided into 2 types. And this more details we'll find in the module number 3, which will commence in another week. So we have CI engines, we have SI engines. CI stands for compression ignition and SI stands for spark ignition. So basic difference between these 2 engines is that the way energy is being dumped from the fuel to produce power. So in fact, if you grossly look an IC engine, we have some piston cylinder arrangement, some charge enters with fuel plus air, and out of this engine we get combustion products, or I'll say exhaust products. And the engine cylinder produces the work W. So the work is nothing but the power output. So you can say it's a kind of open systems. And but the question was, what is the base to CI? So CI means the way energy, the charge, fuel air charge is ignited in a compression ignition, means it is a self-ignition process. During the compression process, the pressure and temperature in this engine cylinder shoots up. As a result, the fuel self-ignites. So that is called as compression ignition method. Spark ignition means that fuel air mixture comes into the engine cylinder. The charge is compressed, but they do not self-ignite. So manually we have to use the spark plug to create to ignite the fuel air mixers. So that is the word spark ignition engines. So more details will be available in the module 3 in this course. Please have patience till that point of time. Thank you. Next questions was in the lecture number 4, where I tried to emphasize the importance of second law efficiency. The problem was, statement was like this: that we have a source, we have a source, we have an engine A which runs between a source temperature of 600 Kelvin and sink temperature of 300 Kelvin. So through this process, we can find its maximum efficiency or Carnot efficiency is 50%, which means beta Carnot is equal to 1 minus T2 by T1. So here T2 is 300 Kelvin, T1 is 600 Kelvin. So for engine A, Carnot efficiency is 50%. But actually, the theoretical or engine efficiency is that based on how much Q H and how much QH is L is rejected, we get that in the theoretical the engine efficiency is calculated eta is equal to 1 minus Q2 by Q1. So in this case, it was given eta for engine A is 30%. So you can see that engine A has actual efficiency is 30% with Carnot efficiency 50%. In same philosophy, but engine B, and through this process, you get work output WA, and similarly for engine engine B, we also get work output WB. But through this process of calculations, we have maximum efficiency based on this data. When source temperature is 1000 Kelvin and sink temperature is 300 Kelvin, so Carnot efficiency is for the engine B can be calculated as 70%. So based on QH and QL data, the engine efficiency would be 30%. But here the emphasis of second law says that whether the engine B is working up to par with respect to its Carnot efficiency or not. Or in other words, engine A has capability of producing 50%, but it produces only 30%. But in the second case, engine B has a capability of 70% producing, but it is actually producing 30%. So although both the engines have same cycle efficiency, but the second law imposes that one of the engine is not doing to its best. So that is the reason the second law efficiency was defined considering Carnot efficiency and actual efficiency taken into account. So based on the data for engine A, the cycle efficiency for the Carnot second law efficiency is defined as actual efficiency by Carnot efficiency. So for that second law efficiency, I'll write this eta second for engine A as 30 by 50. So it is 60%. And second case, second law efficiency for B will be 30 by 70. So it will be 42.85%. So it is that, thank you for your attention that you have corrected this lecture, and accordingly there was some mistakes in the lecture number 4, and the corrected version can be found from this data, from this slide. Another question that was raised in lecture number 2, in one of the numerical problem, I am not getting an answer anywhere in the lecture. What are the entries you put up while finding the enthalpy? So the problem that was looked up is this, which was presented in lecture number 2. A superheated steam, condition is 1.8 megapascal and 400 degrees centigrade. It enters in a nozzle at a flow rate of 5 kg per second leaves at velocity 280 meter per second and at a pressure of 1.4 megapascals. So the question that was asked, and of course heat losses from the nozzle is 2.5 kilojoule per kg. So we know this heat loss from this engine. So heat loss from the nozzle. So here you say heat loss means it is outward. So inlet area of the nozzle is given 0.002 meter squares. So first assumption that we make mass flow rate, that is rho on A1 V1 or rho 1 V1 by small v1, where small v1 is the specific volume. So density is nothing but 1 by V1, that is specific volume. So this from these equations, we know 5 meter per second is the mass flow rate. We know area. We know we do not know the velocity, but we know specific volume. How do you find the specific volume? We have to take the data at the entry stage of the steam. The condition, it is a superheated steam where the pressure P1 is 1.8 megapascal, temperature T1 is 400 degrees centigrade. So I'll tell you how you are going to get it. So at these conditions, you get specific volume was 1.616847. So I have simply used that number here to get the velocity V1. Now using the steady flow energy equations, which we derived in this lecture, from this we have all the data are known. We have m dot is known, H1 is enthalpy for this initial condition is also known. We do not know H2, but V2 leaves at velocity 280 meter per second is also known. Q is also known. So this will give you H2 value. So at the exit condition, what we know is V2, which is 1.4 MPa, and H2, which is calculated from this equation. So knowing these two numbers, we need to find out the exit temperatures. So basically, the data table requires that your complete knowledge how to use the steam table. Now, when there are two coordinates are given, pressure and temperatures, so it is obvious that you should use the superheated data for the steam table. And in fact, in both the cases, exit condition and inlet conditions both have superheated data. So here what I have taken the extracts from a book, steam table book, how you say that, how do you get it? So initial state in this case is 1.8 megapascal, T1 is 400 degrees centigrade. In one of the book, the data that may be available at 1 megapascal, 1.5 megapascal, 2 megapascals. So if you say 1.8 megapascal and T1 400 degrees centigrade, so 1.8 megapascal falls in the range between these two tables, and 400 degrees centigrade goes to lies here for 2 megapascal, 400 degrees centigrade lies here here for 1.5 megapascal. So you have to use this row and this row. And basically, this is where your interpolation takes into account. So based on the data, we need to find where is 1.8. 1.8 megapascal. So means your actual P is 1.8 megapascal. So you have to take the data for 1.5 megapascal, then we have to take the data for 2 megapascal. So maybe for specific volume data can be taken from these two numbers and try to find out what is the relative weightage between these two. So for example, if you say P1 1.5 megapascal, T1 is 400 degrees centigrade. So this will give you P1 as 0.203 kg per meter cube, or meter cube per kg. Now when I take P1 at 2 megapascal and T1 at 400 degrees centigrade, remember both the cases temperature remains same. So P1 is 0.1512 meter cube per kg. P2. So these two. But our actual data here is P is 1.8 megapascal and T is 400 degrees centigrade. So that number that should relatively lie between these two. That is what a intermediate number was taken here. So you can find how far we are away from, how far P is away from 1.5 megapascal linearly, how far P is below 2 megapascal linearly from 2 megapascals. Based on this, we can take this number. Similar process we can find for enthalpy as well. So in same philosophy of calculating initial state, we also can find out the final state of 1.4 megapascal and H2 as 3440. Temperature was approximately estimated to be 380 degrees centigrade. So this is how the linear interpolation works in the steam tables. So these concepts were derived while discussing steam tables in the basic thermodynamics course. This was again lecture number 4, and it was maybe Dr. Pranam Mandal who has taught this course. So unfortunately, he is absent in this lecture. So you can raise this. I can advise him to raise this answer in the forum, or you can come back in the next live sessions. Again, these two lectures are from the other instructors. So as and when they arrive, we can have this discussion, or you can be in touch with the discussion forum so that answers can be given. So this is all about, I want to share the questions in the discussion forum. Now, I invite you to raise any questions. So again, I think I have answered these questions, Mr. A.B. Devil. If this is my part from this question, I have already given the answer. What is the piston cylinder arrangement without a valve or with a valve related to a system? Delete. Okay, so piston cylinder device, when you Normally, piston cylinder devices are very common when we use in the IC engine. So the word valve comes into picture that when some charge enters, so there is a valve. When the charge goes out from the systems, there is a valve. So, for example, in a engine, what normally happens, the fuel and air enters. So it's a charge entry, and that is regulated by a valve. And here it is charge exit, that is regulated by a valve. So what does this valve does? The valve uh, supplies the charge into the engine cylinder in a systematic manner. And this valve is with respect to IC engine, it is, we call this as a kind of mushroom valve, which simply opens in a sequential manner. But your thermodynamic viewpoint is that the what is the what is piston cell arrangement without a valve or with a valve related to a system. So in this case, this system can be considered as an open systems. Okay. Assignment questions are good. Thank you for your compliments. Any other questions? Please raise your hand or write in the chat box. Okay, you have. I think I have explained this in the slide. Maybe this live session will be uploaded, and you can go through that at once. And for more details, you can use any kind of use in the thermodynamics books. Please share your questions. We have almost more than 35 minutes is over. Another 15-20 minutes. We have time. Please raise your questions, queries. My sincere request is to all of you is to participate all the assignments and try to solve them on your own. because it's a very fundamental course with respect to the huge streams of mechanical engineering. Next questions are beyond the critical point. There is continually transforming liquid into vapor without discontinuity. Beyond critical point, there is a continually transforming liquid into vapor without discontinuity. So this is correct. This statement can be said as correct, but what I can say like this, that if you recall our temperature volume diagram, and we have a dome, critical point lies somewhere. We have liquid plus vapor, we have vapor, we have liquid. So beyond this critical point, there is the we can say liquid and vapor, they coexist. And if at all, and they can coexist, and to certain pressure and temperature, still triple point is reached. So I hope I have answered that question. So in the book, you can refer when you look at the properties of pure substance, the key words are critical point and triple point. So at the critical point, we can say the liquid and vapor coexist at same point. But whereas when we say it's a triple point, liquid plus water plus liquid plus solid plus vapor, they can coexist. So these two things is very critical for to discuss about the properties of pure substance. What is your question about this? You have put one slide, ME 204. This is Mr. Sagar. You have put a snapshot of applied thermodynamics of these modules, which consist of the vapor power cycle, compressible flow, steam turbines, reciprocating compressors. But I really do not understand what is your question with respect to the current course. Still, it is not clear to me. Please write your question. Maybe the syllabus is okay, well and good. It's just a syllabus. This live session is with respect to this applied thermodynamics course. Whatever lectures has been delivered or derived or whatever assignments, if there are any queries, you can put it in the forum. And we are there here to discuss with them. We have another 15 minutes. Why HP and LP heaters, high pressure heater and low pressure heater are installed in the thermal power plants. So anyway, this is with respect to other instructor, Dr. Pranam Mandal. But whatever I know or as far as this thing is concerned, high pressure and low pressure heaters, they are actually the part of boiler. So if I can share with respect to some figure, recall your Rankine cycle, temperature, entropy diagram. So the Rankine cycle looks something similar to this. One, two, 3, 4, 5. So 4 to 5 process is a turbine, 5 to 1 is condenser, 1 to 2 is pump, and 2 to 4 is 2 to 3, and then 4 is what we say boiler. So in your question is with respect to 2 to 4. So basically liquid water is being pumped from state 2 to the turbine inlet state 4. And through this process, if you look at the conditions, here it is condition is liquid, here it is condition is superheated. Superheated means it is both pressure as well as temperature has increased. Now from 2 to 3, we require heater that will simply change the liquid state at 2 to 3. So it's just a simple heater taking into liquid to saturated water vapor. Saturated means liquid, compressed air liquid region to simply saturated liquid. And 3 to 4 process is again another 3 to 4 is a 3 to, let's say 3 dash. It's a constant temperature process where phase change takes place. And 3 dash to 4 is again temperature is increases. So the word LP heater, low pressure heater, high pressure heater concept are used here. Now, when you are looking at the low pressure, low temperature region, so use low pressure heater, and where we are going for superheated region, we are doing high pressure heaters. So with that philosophy, the heaters are installed between 2 and 3. Of course, you are true that they are not inside the boiler. They are outside the boiler. But this, if you look at the cyclic diagram, they are just the water is being directed to another heating unit, and from there again it comes to the boiler unit. Then it does this performance. Now when we are looking at the heating systems at the high pressure zone, again it is being fed to these things. So through this process, what we are why you say there is a saving in economy? Because we can use the heat that is get out from the condenser that are being utilized while preheating the liquid water in the from the pump side. So that is the reason we say low pressure and high pressure integrated are different entities. They are not part of the boiler, it is true. But while talking about different entities, they are integrated with respect to boiler. And depending on the high pressure and low pressure regions, whether we want to heat change the temperature of liquid water or high pressure steam, based on that, heater is used. And of course, it is used to save the economy because we are using the heat lost by the condenser and that are being utilized for heating the liquid that is discharged from the pump. This is all about what I understood with respect to boiler and heating system. And for more details, you have to refer the power plant engineering systems, where complete integration of low pressure heater, high pressure heater with respect to boiler can be correlated. This particular course is only the thermodynamic analysis. The next level of this course would be the power plant engineering, where it is completely dealing with the individual entity of a steam or gas power plant or any other power plant systems. But remember, this particular course is again only about the thermodynamic aspects of all kind of power generating systems or power consuming systems, power generating systems. That is what we have: IC engines, gas turbines, their power production unit, refrigeration and air conditioning, their power consuming unit, reciprocating compressors, they also power consumes. So for the compressions, so for all these power consuming and power producing units, this particular course talks about only thermodynamic aspects. That is the essential learning components for this course. So we have another 10 more minutes maximum. So your next question, what is air standard cycle? Air standard cycle is normally referred when you replace the fuel and air systems in the IC engine case. So in an IC engine, what happens? Fuel and air enters into the engine. So normally, if you take the combustion process of fuel and air, it is fuel quantity is about 14 or 15 times higher than the uh, mass of fuel. Sorry, air quantity is 15 times higher because it's a stoichiometric air fuel ratio. So for the thermodynamic analysis, we say that as if air is being used as a working fluid. So this is the first assumption. We say it's a air as a working fluid. Now, with thermodynamic viewpoint, when you say Otto cycle or diesel cycle, where the heat addition process is normally replaced, this heat addition process is replaced with uh, the heat from the fuel is replaced with just an heat addition process. So that is the reason that with that assumptions, the Otto cycle or diesel cycle, they are modeled. So basically it does not take any other fundamental quantities of what fuel it is being used, what is the fuel compositions, whether other stoichiometric condition is maintained or not. The entire concept is just replaced with some kind of air. So that is what, and more details we will find, and it is being explained in the subsequent lecture in the module 3, where IC engine concept was covered. So your bomb calorimeter, okay, bomb calorimeter is of course a closed systems. And if it is a closed system, basically bomb calorimeter is used to measure the by calorimetric principle, you measure the amount of heat in a given systems. We have few more minutes left. I also appreciate your participations. Okay, if there is no more further questions, let us wind up. You are almost approaching the time. Thank you for your attention in the live sessions. And unfortunately, the other instructor was absent. So hopefully, we will see him in the next live sessions. So keep your questions ready during that live sessions. And you are also free to actively participate in the discussion forum. And we will try our best to answer your queries to the best possible extent. Thank you once again for the live sessions, and thank you for your participations. All the best, and thank you.